All right, hello and welcome to week 2. You made it, and last week I know was a bit hectic, just trying to throw a lot of stuff at you, just to review, make sure we're all on the same page, but now that we're all there, we're ready to talk about some new stuff entirely. So we're going to do some more object-oriented programming this week, as well as get into some abstract data types. That's what ADTs stand for. So the goal is more OOP, less oof. That is the idea. Okay, so from last time we talked about constructors in detail, initialization lists. Let us go through all of the things that happen when an object is born, regardless of whether it's on the stack or the heap right now. Let's just pretend it was the stack. This is a local variable called my_c. It is a counter. Okay, so the first thing that happens is memory gets allocated for that object. So in memory, in main's memory specifically, if you want to draw it like this, like here's the stack, here's main, my C just got a box made for it, and I need something a lot bigger than that. So let's just pretend we're inside of main's local variables, we're looking at all of them, and we just made a box called my_c, and we have a counter, and it has memory associated with it. It has count, and I added a vector that we will not use. So here's my example, counter.cpp, called a contrived example because for reasons. And I'll just call this contrived. And it made space for the vector, and we have no clue what the vector needs. It's got magical things inside of it, and we'll actually talk about what stuff vectors have going on in them. But it made space for all the stuff that a vector needed when it was initially starting out. And so now we have room. We've got space. It's been made for us, brand new and shiny. Okay, so this is our my_c at the moment, fresh off the line. The next thing that happens is the appropriate constructor is called. Now that we have memory to work with, let's fill it in with stuff that the constructor asks us to fill in. So if we go to the constructor, it's going to take an int parameter for initial count and start working. So the first thing that's going to do is the initialization list. That's the first thing that happens, and that will initialize any member variables with this constructor style syntax. So it'll set count to whatever initial count is that was passed along. And so in this case it's 42. And so the first thing that's going to happen now is count gets 42. Okay? So that is any member variables mentioned in the initializer list get initialized. Any non-primitive member variables not mentioned in the initializer list have their default constructor called, and that is a very large sentence with a lot of information. So a non-primitive type, well, it's easier to talk about primitive types. Primitive types are things like int, bool, double, char, things like that. So not string, it's non-classes. Those are primitive types. Array of any type is a primitive type. And let's make this italic so that it looks different. So that's what primitive types are. And because we initialized our one primitive type, our int inside of our counter, we're all set there. That's not going to have to be worried about anymore, because if you don't set it in the initializer list, it's just set to random garbage memory values, as you know, when you declare something of type int and don't set it to a value. Okay. Vector, on the other hand, this contrived example vector, is not initialized in the initializer list. And so, before the body gets executed, contrived example has its default constructor called. So it's as if we said, if it was like a stack variable, we said, just like that, declare it, and it's just initialized to whatever the empty vector is for ints. Okay? That's its default constructor being called. And then finally we hit the body. The body of the constructor is executed to perform anything else that you need doing. So for example, here I just put a cout statement. So after initial count has been set, you could actually print it out here if you wanted to, and it'll be the right value. After count is set to initial count, I mean, then this cout statement will run. Okay, so that's the final thing, the body of this constructor gets run and does anything else you need it to do. Okay, so that is the birth of an object. Hopefully that makes sense. And then you have all these nice variables. Remember, variables have been set up at this point, and you can use your object as you wish. That is the idea. Okay, moving on. And before we get into today's stuff, I also want to just tell you briefly, maybe you're not too familiar with the terminal, and I encourage you to read that optional reading about that and come to office hours and ask me anything you want about it. But that's something that I will going to have to ask you to use for this semester, so I will help you as much as you need. I can send you my CSCI 40 videos if you'd like, whatever you need. But yeah, you're going to get comfortable with the terminal for compiling, for moving around, things like that. One thing you're not technically required to do in the terminal this semester is edit. So I have installed on your virtual machine. You just click these boxes in the bottom left, these 9 little grid thing of 9 boxes, and you can scroll down, find Visual Studio Code, and you can drag it onto your little dock thing if you want. But this is a graphical editor that you are welcome to use if you would prefer it. And then you can just go to like File Open or drag a file that you care about. I'll open my counter file, for example. Dun dun dun. There, in my home folder, Windows Desktop code from class 41, lecture 3, counter.cpp. And it'll be nice and pretty, and maybe you can make it bigger. And you want to install this extension, of course, things like that. But yeah, it's fun stuff. It'll be useful. If you would like it, just click yes to whatever. Go back to the file, get rid of that. And now you have fun things. Autocomplete. Hey, beautiful. Okay, so that is that. Feel free to use that if you would prefer. You can actually drag a folder as well and see like all the files in the folder. It's kind of like this thing in Vim. See what's in your folder. Okay. So I don't know if I changed anything, but we're gonna just reload this file in case. Alright, now we're back. Okie dokie, so yeah, use that if you'd like, and let's get into today now. So here are my goals for you for this set of slides. We probably won't get to all of them today. But first, let's talk about a library file that you might not have used before that I'm asking you to use in your lab that's due this week. Okay, so let's look at all the stuff about SStream. So you could just search C++ SStream, and the first thing is your C++.com documentation, and this will be your favorite place to live. There's also cppreference.com, which is like a competing website with documentation. I grew up on this one, so feel free to look at whichever, or both. And probably the place that you usually want to go is you're looking at the header right now. This is SStream, and we see what's inside. And I'm asking you to use a specific type inside of SStream, this class called StringStream. And so just play around, look at these. This is probably the most useful. And so this is going to now tell you, if you've never been to this website before, maybe I can make it bigger. Oops. Not the right kind of bigger. There we go. It'll tell you all the things that are going on in this class, all the operators that are involved on objects of the type StringStream. And yeah, probably the best place to go when you're looking at a type that you don't know is go click on the constructor, and then it'll tell you how you can make all of these things, okay? And there is a default constructor. You can see this has initial values that might look a little scary, but that's okay. Scroll down and you'll see a nice example, and usually any page will have a very nice example of what's going on. Okay, so this is actually kind of what I want to show you, so let's build this up together perhaps. So StringStream is like your own personal cout. So I'm going to make a new file called SStream, I guess, .cpp. So include iostream, so we'll eventually print stuff out. include SStream, this is for string stream, and using namespace standard, of course, as we know and love. Alright, so the idea is we like this SStream because it allows us to make our own little personal cout. You can put stuff inside it, you can send it data, you can retrieve data out of it, whatever you're into. String stream will work for you. So string stream, SS is like the default way of saying it. Let's make a new empty string stream object. So now we've got one, and we can shove information inside of it, pretending like it's cout. It has that operator defined on it. So we can send it 42. We can send it a space. We can send it 43. And that's that. Okay, so now I'm going to compile and run this, I guess. We remember how to compile all our stuff, right? We go to, here's my file, it's in this folder, G++, standard equals C++17. We want the cool new stuff. SStream.cpp-o, what I want it to be called. SStream. And now it's in that folder now, it got compiled. There it is, /SStream to run it. And nothing happened because this did nothing. This is not cout, it's its own little variable. And so inside of it right now, inside of our SS, it's got some kind of little buffer thing, and it has stored the characters, in essence, 4, then 2, then space, then 4, then 3. So that's what's going on inside of SS right now. Maybe it's like buffer, that's its member variable. We'd have to look at the implementation of string stream, but we don't have time for that. And it differs by who you're using. Okay. So, no idea why this is complaining. Dun, dun, dun. So, what we can do is then get stuff back out of it. We can pretend that it is both cin and cout. So we can say int first num, and then second num, make space for these things. Then we can extract information from that string stream. So get the first number, then get the second number, which is nice, because now we have those things. Okay? And then we can print out what's going on here. Unqualified ID. Yeah, this is probably the little parser inside of Vim. Probably didn't like that I had a comment on that line, maybe? No idea. It's not important, though, as long as it works. Okay. So, again, compile and run. We've done nothing. We've not output anything. But now first num and second num have been set to 42 and 43. Because we put them in the string stream, then we got them out. So we can print those. Okay. This is just a quick little thing that you can see here. And also, the thing that we're using in the lab for your tests is extraction. So we put this string inside of string stream. How do we see the string that we just built up? Well, actually, let's go to the docs. It is this stir member function, and we can click on that one, and or you can just find it on here, wherever it may be. Get and set content. All right. So what it does, this is the declaration of this function inside the class. It returns a string. A constant string, or no, sorry, just a normal string, but it's a constant member function. It's a getter inside of the string stream class, and it returns the string that was inside of that. It looks like there's a overloaded one called stir also that when you give it a string, it sets that string to what you passed along. Okay, So we're just going to call the one without any arguments, and that'll get the string out for us that was inside. Okay, so I put 42 space 43. And so now I can go and view the contents of that buffer that was inside of SStream. I guess I need string. You can look at the string you've built up inside SStream. Because what it's doing is it's storing 42. So it stores everything as a string, and the name implies that, is set to this string. 42 space 43. These are characters, not numbers anymore. And this used to be the way that you actually took a string and converted it like to an int. There are better ways to do it in C++ now. Okay, so we can get that string out by saying ss.stir. Okay. We'll call this SS contents, and we can see out that. And it will look exactly the same as this line down here, so there's no real reason to keep it the way that it was. We'll say like first num, colon perhaps, first num, then second num, colon space. How about that? Okay, so we extracted the contents of SStream, the stuff that we put inside, and remember that it was all converted to strings deep down. Okay, so the .stir command gets the string out that you had built up with using these calls to the insertion operator. Okay, that is, I think, all I want to say about SStream and the SStream header. All right, now let's get into arrays, and let me check the time real quick. Arrays and dynamic allocation. So, just in case it's been a while, sorry if you watched the review video, and I'm talking about this again. This is very important, so I'm going to remind you extra. So an array is just, it's a variable, it's a thing that holds a bunch of stuff. So here's my array ARR, and all that stuff has to be of the same type. Okay, so these are all ints, for example. And so each item, it's called an element, it has an index 0, 1, and 2, things like that. It should be all coming back to you now. And it's directly accessible. So this is what the memory looks like deep down, and how you access things is, if you want the 1, you're going to say ARR 0, okay? That's exactly what you do. And this is how you declare an array with a certain size and a certain type. So this is an array of 50 things, and those 50 things have to be ints. Okay, so that's an array in a nutshell. Let's get back to the normal color. And so that is, this syntax right here is how you declare an array on the stack. So it's just a local variable. So whenever I say stack, I mean local variable. And that means, like, for example, if I'm in main, and I say int ARR of size 42, ... What just happened is when I run the program, I have my function call stack. Main just got called by like the terminal or somebody. Now I have a local variable called ARR. It lives on the stack, and it belongs to main. Okay? So that's what it'll look like in memory. That's the idea. So this is how you declare an array on the stack. To initialize an array, you have a few options. You can do it all in one fell swoop. You can say int ARR equals, int ARR bracket bracket equals the contents, and then it'll set the size to whatever the content size was, so you don't have to put it twice. So this is equivalent to putting a 3 here. You didn't have to do it. Or you can do it like we did over here. You can declare and initialize. So you can say int ARR of size 3, semicolon. Then you can start initializing things like ARR 0 equals 1, ARR 1 equals 2, ARR 2 equals 3. And so that'll set it up just like that. Okay? That is how you declare and initialize arrays of a certain type. Always got to specify that type on the stack. Okay? Now, a bit of a secret, and we talk about pointers. So arrays are really pointers to their first elements, which is a weird concept, but it does make sense, and it will make a lot more sense when we talk about how to declare or how to get an array made for you on the heap. So here's an array, and we use these fancy bracket syntax, this fancy bracket syntax to initialize the array, but really, even though I draw the array like this is the standard way of drawing an array, it has the name R, it has these contents, really deep down inside, the variable, when used by itself, ARR, is secretly a pointer. It knows the starting address of this array, perhaps it was 100. ARR will store 100 and point to the very beginning of the array, which is insane, okay? Just keep that in mind. It knows the starting address, okay? So, ARR holds starting address of where it starts in memory. It's really a pointer, okay? So, you can do things like int star p equals ARR without any brackets. This will just make p hold the same thing as ARR, which was really a secret pointer. And so now p is also pointing to the beginning of this array. You see that? Let me give you some examples and prove it to you. So, honestly, let's just copy a lot of this. Whee! That's all we really need. Okay, so here's my favorite array. Got to make it pretty. And I'm going to print out ARR. No brackets. So let's go and compile this. Oh no. And it just got compiled. Let's run it now. /arrays. Oh man, was that secretly a pointer? And if I rerun this, it'll get made in different places because your program gets loaded in different places in memory as you run it. Okay, what can we do with this? Well, we can start doing this. Int star p equals ARR. P also points to the start of the array. And so now, you never thought you would want to do this, but now you can. See out p, you can use the brackets on a pointer to an int and say that. Treat it like an array, because it really is pointing to one. It knows what to do. It'll output the element there, which is really ARR0, or ARR1, sorry. But it doesn't matter, okay? That's the idea. Or maybe I can say same as ARR1, which is a bit weird, and this is useful before we get to the heap. It's useful to because it means that these two functions, no matter what, are going to be the same. So you can take you can make an array. You can make a function that takes an array, sorry, using this syntax. Ask it for the array with brackets, or you can ask for the array with a pointer to the type stored inside that array. Okay? So those are both a thing. And then also just a warning. Arrays don't know their size. So just remember to always pass along that size if you ever need it. Okay? There's no dot size for arrays. They're a primitive type. Okay. Well, let's get to the heap now. So we're going to create and delete arrays on the heap. We know how to create and delete normal single things. We can say int star I equals new int. So this makes a brand new int for us on the heap. And so here's the stack where our local variables live. Here's the heap. I is a pointer to some brand new int on the heap. Okay, maybe this was address 108. I holds 108. It is a pointer to that brand new place on the heap that is fresh and beautiful. Okay? That's a single int, though. We want to make arrays of a certain type. So if you want to make an array, you have to use pointers again, and this is why I built up to this. So int star arr equals new int of a certain size, like that. Okay, so this makes an array, which is really just a pointer, remember? This is maybe 112. Boop, and at address 112 starts an array with 3 things that was made fresh for us on the heap. Okay? And remember, all this stuff is uninitialized currently. These are question marks. Okay, we've just created an array on the heap. How do we get rid of it? Well, in order to get rid of a normal single int, you say delete I. You delete the pointer to it. And so it goes, follows that pointer, finds it in the heap, finds that int that you made before, gets rid of it. Okay, so delete I will delete that thing. So now it's gone. And then, or maybe red's a better color for this. Yeah, red please. Thank you. So now it's gone by saying this. Well, if you want to do the same, the C++ compiler is not smart enough to know the difference between if you give it a pointer to an array or you give it a pointer to just a single int, because see how the types are exactly the same in those cases. In order to tell the C++ compiler I'm about to delete an array that I made on the heap for myself at one point, you're going to say delete bracket bracket arr. Okay? So by saying that, then it goes, finds that entire array, deletes the whole thing. Otherwise, it would have just deleted the first element. Okay, I hope that makes sense. That's the idea for that. And so if we want to make an array on the heap now, we can say int star heap array. And so this pointer is going to get set to the starting address of this array that we're making for ourselves. New int of a certain size, 42. And then you can start setting things there. So dot dot dot. And once you're done with it, delete it with those brackets. Okay? Okay, so that's the idea. And that's all I wanted to say there. So the reason I'm building up to this is because we're going to talk about vectors. And it just so happens that vectors and strings and many other things, many other library types, are secretly using dynamically allocated arrays, which means arrays allocated on the heap. For strings, it's dynamically allocating an array of characters. For vectors, it's dynamically allocating an array of whatever type that vector holds. Okay? So you really have been using the heap all this time, even if you hated it and you didn't like using it manually. Okay? You have used it and enjoyed it. So there's that. Okay, checking time. Now, before we get into vectors, I want to talk about algorithms and data structures, because you know what an array is. It's a data structure, and we want to generalize this idea and invent more eventually. And then also differentiate between things called data structures and things called ADTs, or abstract data types. That is the idea. So let's get started. These are some of these terms I'm sure you've seen before, like algorithm. It's just a sequence of steps to get at some answer, to solve a problem, calculate something, I like to introduce it in my CSCI 40 class as like a recipe. It's like how you make peanut butter and jelly, for example. Okay, so that's all an algorithm is. I'm sure you've seen that before, but just a refresher. Now, computational complexity, which is just a large word for no good reason, it is the amount of resources used by a program, and that could be memory, or it could be time. Mostly, we care about time. We have a lot of memory in our computers, but we're going to talk about both in this class. So, how long does it take to execute this program? If it's going to take until the end of my life, there's no use running it. And if this program needs so much memory to do what it needs to do, like naive ways to calculate primes, for example, well, it would need so much memory that I can't afford that. There's not enough space in the universe to store all of those transistors. So we're going to have to find a new algorithm, perhaps, that solves things with a better space complexity, a better time complexity. Okay, that's the idea. And so you'll hear those words. You'll hear words like time complexity or space complexity. All right, so we'll just plop those words together like that. And I think it's logical and a good idea to look into these things, because if we could write our programs to be faster, I think everybody would want that. If we could write our programs to work for more users who don't have as much memory installed on their computer, we would want to reach out to them. Okay? And then finally, another kind of name for this is algorithm efficiency. How good are our algorithms? How efficient are they in terms of time and memory? And there's other things you can think of as well. So this is measured by computational complexity. Okay, so just some terms. This might be a little dry for a second, but we'll get to the good stuff in a second. Okay, so a data structure. You know and love data structures already. You have used arrays. Okay, so a data structure is a way of organizing things. Okay, it's a way of structuring data. Oh, yes, it's self-explanatory, kind of. So if you have a bunch of ints and you want to put them all next to each other, you don't go and make like a bunch of int variables. You don't say int x, int y, z, p, q, w. If you want to store 6 things, no, you make an array. You say, no, I want to make an array of 6 things, and now I don't have to put them all next to each other. Okay, I would much prefer not to have to deal with remembering all these different variable names. This array puts all these ints next to each other like I wanted, and that's all I need. They don't need individual names, for example. Okay, so the idea about data structures, the thing that I want to drill into your minds is you know exactly what the memory looks like for a data structure. That is something you can touch. Okay, and so for example with an array, you know that it's a bunch of ints laid out next to each other in memory, one after the other, with a certain starting address, for example 100. And I gotta give myself some room for that if I want to draw that. So here's our array ARR, and it starts at address 100, for example. Okay, that's a bad A. Okay, now I'm happy. All right. Now an abstract data type, or an ADT, an abstract data type, is a data type described by predefined user operations. So it's essentially a class. So you're going to make these operations that live inside of it, and it has these classy kind of ideas where you don't know how it's implemented as the user. Like you get these public things, but you don't know about the private implementation. You don't know about those member variables that the implementer of this library, of this abstract data type, has given to you and doesn't want you to touch. So think like all the public stuff that you get in a class. Example, a class with public / private stuff. So you don't know the basic data types that are used to make this abstract data type that you're using. You don't know if it has an int inside of it. You don't know if it has an array inside of it. You just know what you get from the public member functions, okay? That's the idea. And so think vector. And I'll talk about why you should think vector in just a second. Even though a vector kind of seems like an array in a sense. A vector is an abstract data type, okay? And when you see an abstract data type, at least in this class, in the textbook, it'll be underneath the definition of that data type. It will start listing all the operations and common data structure operations, because data, we're putting stuff in, taking stuff out. You have things like access, update, search, insert, remove. And so for a vector, for example, we can just go to the docs very quickly, because I want to actually make sure you know how to use all this stuff. So on the left-hand side, up here in reference is all the headers, and vector is in containers. It holds stuff, contains stuff. It's like a bucket. And then here's the vector class, and here's all the stuff that a vector has. Here are all of its member functions, okay? And so for example, if we want to access an element of a vector, you can use the array-like operator that exists, but it's much better, it's much safer to use at for reasons. And it throws an exception, in fact, if you try and access off the end of a vector if you use at. So this is .at. And update is also .at, actually, because you can say .at, I don't know, 0 equals something. So it's the difference between like getting the value and setting the value. .at does both because it returns a reference. So let's say like, I don't know, v.at 0, print it out. Alternatively, for update, v.at 1 equals 2. Okay, that's the idea. You can use at for both. Search, let's see. There might be something in algorithm that does this, but I can't remember immediately if vector itself has a search function. Probably has a find somewhere. No, it's not like string, I don't think. No, yeah, so there's something in algorithm, I think, to go and search through a vector, but vector itself does not have a search function. Insert and remove, you have, for example, pushback for insert, and erase for remove. Okay, and I encourage you to look at all of those functions and see just how they're meant to be used with the library documentation. It'll give you a nice, cute little example, and hopefully that's helpful. This will be where you live a lot this semester. Okay, so data structures, arrays, abstract data types, vectors. What's the real difference? Okay, so again, for data structures, you know exactly what's going on inside of that array. You know that your ARR, it lives starting at address 100. If it holds ints, the next int is 104. The next int is 108 after that. 1, 2, 3. And you can touch this memory. You know where it is. This is all it takes to be an array. It's just a bunch of places in memory. Exactly what's happening, you get to control. Okay, you can say ARR 0 ++, something like that. Okay, and touch the memory. There is nothing about an array you don't know what's going on. There's no documentation you have to read, things like that. It is memory itself. Whereas, for a vector, you're kind of given a black box. That's what a class is. It allows for public things. You can only touch the public parts of a vector. Here's my vector v, or vec, for example. And you can ask it nicely to do things. You can say .pushback 3 for me, please, vector. And I can be like, you got it, dude. But you don't know what's happening in memory. Perhaps the vector is implemented like this. Perhaps the vector really stores just a really long string with all of the elements. 1, comma, with commas in between. 3. And when you say for it to do something, pushback, oh, pushback. That's an interesting misspelling. Sorry about that. when you say pushback 3, perhaps it goes into this little string and puts another 3 there, adds to the end of it, and a comma. Okay, it doesn't have to be an array deep down. It could be a string for all you care. You just interact with a vector like, all right, DotAt index 3. Well, it'll extract from its little string, perhaps, a number, convert it to an int, and give it back to you. That could be a vector, okay? You've been kept in the dark. It's a black box, okay? That's what an abstract data type is. Emphasis on the abstract part, okay? That is key. So you don't know what memory looks like deep down. You just know about the operations. So an abstract data type is all about the operations. Okay? Whereas a data structure is all about the memory. Okay, all about the data, for example. Okay, so I've made a long slide with a lot of words that specifically say what's going on and the difference. So a vector doesn't have to have an array inside of it. It could be that string. It could be a different data structure that we'll talk about called a linked list. It could be whatever. The data structure that implements an abstract data type, and that is the key. This sentence right here is the key. It's not important. Here I use data structure and ADT in the same sentence, and this is the idea. Okay? What makes a vector is that here are its operations that is guaranteed to have no matter which vector somebody implements for you. It has to have these things. That's what a vector means. And they do what you expect if you do them in a certain order. Okay? Like we were talking about over here. That's what it means to have an abstract data type. So it's an idea. And you can use data structures, okay? You can use data structures to implement abstract data types and have the operations work in a certain way, okay? So abstract data type is all about the operations that are defined. The underlying implementation doesn't matter. Let me drag this up here. Okay, so you, in essence, if I want to put this in one big slide that says what I'm trying to say, it is this. ADTs are implemented using data structures. Okay? So the data that's inside an ADT, those are your data structures. Okay? That's all I want to say. And let's take a look at the time. All right, let's start talking about vectors now. So vectors really aren't implemented with weird strings inside. That's kind of silly. What they are implemented with is dynamic arrays, okay? And so in your lab, you will be implementing the vector abstract data type, the operations that I have told you to define, okay? For example, pushback, size, and at. Those are the member functions. So let's make sure we understand what all of these things mean. So here's my vector. Oops, let's have a normal color now. Here's my vector. I make one. Vector, let me just use the standard vector for now. But you will be implementing your own. Oh darn, it gives the wrong color. Sorry about that. All right, so vector int, for example, v. What just happened now is the way we can think about it. We don't know how it's implemented, but in essence, v holds something that is currently empty. Okay, there's nothing there. Okay, v is right now empty. And when I say v.pushback, and there I go again trying to spell it wrong, pushback 1, now whatever underlying data structure that was inside of this vector got changed. Now it holds just a 1, okay, and nothing else. There's nothing after it, okay? And if I were to say size now, v.size, that would give me back 1, because there's one thing in the vector. It would go and it would look at what it has, see how much stuff it has. Okay? So that's what size would give back. And then at will allow for me to get an element at a certain index and also set it. So if I say v.at0 equals, I don't know, 2, this would go into the vector wherever it's storing its first element, reset it to hold 2. Okay? Or if you want to just print it out, you could say cout v.at0. That's the idea. So, I hope that that makes enough sense. These are the operations that you will be implementing, and we'll talk about each of them, okay? So, really, if we want to get into implementation decisions, a vector secretly holds a dynamic array. It has some other stuff. Secretly holds a dynamic array that initially is set to hold just one value, okay? And dynamic, it means it's on the heap. Initially, it only holds one thing, okay? That's the idea. So that is a vector. And so we're going to implement vectors using arrays as an underlying representation, okay? So I won't write too much code because you will be implementing this, but this is what's going to happen. So all of the elements that you push back to your vector are going to be in this dynamic array that you store on the heap. Okay, so there are going to be a few different private member variables. All right, in addition to the array. So this is how we will implement our vectors. Okay, so the vector class, its private member variables will hold these things. So each vector gets a pointer to the current array on the heap. Okay, and so here's the heap over here, for example. It's pointing off to that wherever it's storing its array, and then it also stores the current size, so you can just immediately return it. Maybe it starts out holding, I don't know, or in this example it holds like 1, 2, 3, 4, 5 things. Or actually, no. Let's say it holds 3 things. And then it also has a current capacity. And this is why dynamicness is useful. So let me make this a bit bigger. Doop. Capacity means how much the array can hold at the moment, how big that array is. So right now it can hold 1, 2, 3, 4, 5 things. But maybe it's only using 3. 1, 2, 3. And this is like empty, and this is empty. That's the idea. Okay? So, in your constructor, for your vector, and the name of the class is going to be vector with a capital V in this case, it's going to, in its constructor, initialize the current size to start out at 0, because there's nothing in the array to begin with. It's an empty vector, but it can potentially hold one thing. That's what the capacity means. The current array the current dynamic array, and we might have to replace it, holds capacity things. Or can hold. Maybe I should say can fit. You can fit capacity many things. Okay? So right now, for this example that I drew, this v vector has a certain array made on the heap. Right now it has size 3, which means the first 3 indices are in use. And it has capacity 5, which means it could grow to hold 2 extra things if it needed to, okay, without having to change this underlying array. And the big thing about vectors is if our current array doesn't have enough space, we make a new one. This is why the heap is key here. Okay, I think let's make that bold. That's what I wanted to say for this. Maybe these are a little too close together for my liking. How about that? All right. Now, let's see how we're doing on time. Yeah, we got a little bit. Now, let's talk about the .at member function. And actually, let me go to your starter code just quickly. That would be helpful here, I think. So I'm gonna get out of this, and then I'm gonna, I guess, make a new tab on my terminal, and let me go to. Did I put it there? No, I have. It's on my Windows desktop, my starter code folder. It's CSCI 41. It's lab 01. All right. So here is your vector from your lab. This is what it looks like. Okay, it's called vec with a capital V, and it has a constructor, has a pushback function, has a size, has an at that returns a vector reference or an int reference, so that you can actually change as well as get back the value. Then also a sort function. Okay, and here are some private member variables and methods that you will be using. Okay, so that is the idea. This is what will happen. You will implement these things using these kinds of using these method names and those private member variables. Okay, so let's talk about the .at function. So because you're vector, you know it has this array inside of it. You can just access it. Okay, so all you have to do for the .at function, it's a very quick thing to implement, is you just have to return the value that's at that index in that array. Because deep down, your vector, it's going to look like this. It has the array, which is a pointer onto the heap, into some actual array with a certain capacity and a certain size. And here, it'll be called num items and capacity. So let me try and do that. Okay, and so perhaps the capacity is definitely 3 given my drawing. Maybe the num items is just 1. It holds 1 at the start. Okay, so .at is going to go, if I say .at of 0, for example, what it's going to do is this function, when you implement it, it will go inside the array and just access the element there. So it'll say something like, will turn into like array 0 and give that back. Okay, and one tricky thing is it's going to return a reference to an int, which you don't have to do anything extra. You can just return the int as normal, but it'll be given back as a reference. Okay. By virtue of its type. Okay, and the reason you would want to do that is so that you can do this. You want to say something v.at 0 equals 2. Okay, and so the reason we give back a reference is because this will return a reference to array 0, 2 R's. And then, because it's a reference, you can reset it. You see that? That's super nice. Otherwise, you can only just get it back, because if you change this to not have this ampersand, then suddenly you're just returning a new int, a brand new int that does nothing. Okay? Okay. So that is that. That is your .at function. Another easy one is .size. If I go in and copy most of this, let me show you. No, I would like to copy, please. Give me the lasso. There we go. All right. So I'm going to copy that, plop it there, and again, sorry about that, it is num items. So size is just a getter. And for some reason, it didn't copy the P. Sorry about that. So all you have to do for .size is return the num items, the number of things in the current vector. And that's, remember, different from the capacity, because the capacity is the potential of the array to hold things. It has room for extras if you do pushback, which we'll get into, but right now, it's as if it were just an array with one thing. Okay? That's how we're displaying it to the user. Okay? That's what we want the user to think about and have in their mind. Okay? So return our num items, not our capacity. So the whole purpose of an abstract data type is you're like tricking the user into thinking that it looks a certain way. So we're kind of tricking the user to think that there's just an array with, in this example, one thing right now. When in reality, this array that we're using to store the user's data actually has room for two more things. Okay, but we don't want the user to see that. We want to return num items being 1 and make the user think that there's just an array with one thing in it. Okay, that is the idea. We're making the user's life easier. That's what it means to be an abstract data type. We give them these operations, and that's all they get to see. They don't have to care about how we went and implemented our .at function, our .size function. Okay, again, we could have totally used a weird looking string and got the same stuff. As long as we implemented .at, .size, .pushback appropriately, we can put whatever we want inside of our vector implementation. Our underlying representation does not have to change, or does not have to be some set thing. Okay? So, gosh, do I want to save pushback for next time? Let's do this. Let me do pushback just briefly, and then we'll go through it in detail next time. How about that? So, this one's the hard one. So the idea is, pretend we have our vector v, and remember all its stuff that it has. It has that array inside of it, it has its num items, it has its capacity. When we're about to push back, add a new thing to the end of our vector, just keep calling it v, I guess. Perhaps we are in this situation where our array holds three things. I'll just call it size and cap. It holds three things, and its capacity is three things, and right now we're asking to push back to it. Okay? There is no room because the size is equal to the capacity. You see that? So there's no fourth thing right now, and it would be undefined behavior and incorrect to try and access past the end of that array. Okay? So this is where the magic happens. Inside of pushback, what happens is, magically, before the user's eyes, we delete this entire array. But not before we copy it into a 2 times bigger array. Okay? So if our current capacity is 3, it will never get to be that in our example, in our actual implementation, but assume it was 3. We will make a size 6 array now. 1, 2, 3. A size 6 array, change array to point to that, and then size stays 3, capacity has now doubled to 6, and then, let's see, you're about to push one more thing, so you're going to push back perhaps 4. You're going to put the 4 where it needs to go now because you have room, and you'll increase your size. Okay? So that is pushback when resizing needs to happen in a nutshell, and I will go through that a bit slower in the next lecture. Okay? So I will see you back for more of pushback.